Hello everyone, welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about the open system, energy balance on open system. In the previous lecture we have discussed about the closed system. Closed system are those systems which are close to masses, but it can be open to energy. But open system are those systems which are open to mass and energy both. So there is a difference between open and closed system. So open system are open to mass and energy also. So for example, this is an open system. This is a compressor. Compressor is an open system. This is a pipe. This is an open system. This is pump. This is open system. This is a channel. So this is a channel for flow of water. This is an open system. This compressor compresses the gas. Suppose the gas is entering. Point 1, it compresses the gases. So air pressure P1, air pressure is P2. Enthalpy of the gas here is H1 and here is it H2. So this is an open system. Similarly, this is a pipe. Suppose some mass flow rate of water is entering to the pipe and mass flow rate of water out from the pipe. So this is an open system. Heat can also enter through the sides of the pipe. Through this surface area. Similarly, this is a closed. Similarly, this is a channel, confined channel, or the flow of fluid through a channel. So this is an open system. This is a pump. The pressure here is P1, pressure here is P2. So this is temperature here is P1, here is P2. So again this is enthalpy, here is H1, here is H2. So this is an open system. We will derive first of all we will derive the general energy balance equation, and from then we will apply the general energy balance to these systems. So we can once we derive the general energy balance equation, then we can use the general energy balance for these open system. There are various other open system like distillation column. The fluid is entering. This is the top product. This is the bottom product. We can apply the energy balance on any open system. So let's derive first of all we will derive the energy balance equation. So this is a control volume. Figure number 1 is about control volume. This figure is about the control volume. This is a system. The fluid which enter to the system at point number 1 has a mass. The mass flow rate of the fluid which enter to the system at point number 1 is m dot in. So mass flow rate of the fluid entering to the system at point number 1 is this. Similarly, the mass flow rate of fluid which leave the system at point number 2 is this. The height, this is the reference point, this one. Here height is equal to 0. This is Z1. This is Z1. This is Z2. This is Z2. This is Z2. Z2. Height of point 2. Similarly, velocity of the fluid at point number 1 is V1. The internal energy of fluid at point number 1 is U1. The height of the fluid at point number 1 is Z1. So this mass flow rate will consist of this mass flow rate will possess 3 types of energy. One, it will possess kinetic energy due to its motion, due to its velocity, and due to its mass. Similarly, this mass flow rate will possess internal energy due to the molecular motion, kinetic and vibrational motion of the molecule which are present in the fluid which passes through this area. Similarly, this fluid will present at some height. The fluid is present at some height, Z1. So due to its height, it will possess some potential energy also. Similarly, this fluid which leave the system will also possess 3 types of energy. One is kinetic energy, one is internal, and other is the height energy, which is the potential energy. The internal energy of the molecule are atoms which are present in the fluid element, and the velocity energy, which is the kinetic energy of the fluid which is doing the system at this point, and this is the system. Similarly, there is some another energy which is heat, which is entering to the system. This is Q dot, and some stirrer also doing work in the system. So the stirrer work done by stirrer on the system is W. Yes, this is the stirrer work. So this is some stirrer. A stirrer is also stirring the system. So the stirrer work is WS dot. So this is the stirrer work. So the general energy balance equation for this open system will be derived as, this is the general energy balance equation. This one is the general energy balance equation. Energy flow rate N, energy flow rate out, energy flow rate N minus energy flow rate out plus energy generation rate minus energy consumption is equal to energy accumulation rate. So this is a rate base equation. The dot shows the rate base. Rate means per unit time. So energy per unit time equal to energy dot. So if there is no chemical reaction, then the energy generation and energy consumption term will be 0. So there is no chemical reaction, energy rate enter to the system and minus energy out from the system will be equal to energy accumulated in the system, and it will become equation number 1 will become equation number 2 after the simplification. Now from figure number 1, if the entering energy are Qn, yes, the heat was entered to the system, which is Qn. This was Qn. This is Qn. This one. Similarly, Ws, this is the stirrer work. This Ws is the stirrer work. Work done by the stirrer. This. Work done by the stirrer. This. Stirrer work or this stirrer work. So Ws energy, the work done on system by stirrer. Ws heat entered to the system. Qn is the heat entered to the system from surrounding. Ws is the shaft work or stirrer work. It can be pedal work, it can be compressor work, it can be the heater work. Heater work which is doing some heating. If there is some heating element, it will be heater work. So this shaft work is denoted by Ws dot. So the shaft work. Similarly, if the mass flow rate which enter to the system is equal to the mass flow rate of fluid enter to the system carry, if similarly if the mass flow rate which enter to the system carry some energy, so similarly the mass flow rate of the fluid which enter to the system carry with itself some energy. And what are these energy? The mass of the fluid which enter to the system, like this one, mass of the fluid which enter to the system, this one, mass of the fluid which enter to the system, it will carry with itself some energy. One energy will be kinetic energy, the other will be internal, and the third one will be potential energy. Similarly, the mass of the fluid which leaving the system at this position at point number 2 will carry with itself the kinetic energy, the internal energy, and the potential energy. So mass of the fluid which come out from the system will carry these 3 types of energy. So similarly the mass flow rate of the fluid which enter to the system carry with itself kinetic energy, potential energy, internal energy. So mass of the fluid which enter the system carry with itself 3 types of energy: kinetic, potential, and internal energy. So the mass of the fluid which enter to the system and which carry the energy are denoted by this one. The mass per unit time, mass of the fluid which enter to the system per unit time. This dot is for the per unit time. And this is the velocity of the fluid which enter to the system at point number 1. This one is point number 1. This is point number 1. This is point number 1. This is point number 1, and this is outlet is point number 2. So this is point number 2. So this is the kinetic energy. This one is the kinetic energy. This is the potential energy. Z1 is the height at point number 1, and this is the internal energy at point number 1. Similarly, the mass flow rate M out is the mass flow rate of the outlet liquid the mass flow rate of the outlet liquid carry with itself three types of energy. One is the kinetic energy at point number 2, potential energy at point number 2, the internal energy at point number 3, at point number 2. So this is the kinetic energy at point number 2, this is the kinetic energy, this is the internal, and this is the potential energy at point number 2. So now the kinetic energy at point number 2 is this one. This is of mass flow rate of the outlet liquid at point number 2, and this is the velocity at point number 2. So velocity v2, and this is the square. Half mv square is the kinetic energy. Half mv square, as we know, half mv square is kinetic energy. Similarly, potential energy is mass flow rate of the outlet liquid at point number 2, and this is the g. Acceleration due to gravity, its value is 9.8 meter per second square, or 10 meter per second square. Similarly, this is the z2 height at point number 2, and this is the internal energy at point 2, and this is the outlet mass flow rate. So at the inlet, similarly at the inlet, we have already discussed at the inlet the mass flow rate carry kinetic energy at point number 1, potential energy at point number 1, and internal energy at point number 1, as we have already discussed this. As we already discussed this point, we have already discussed at this point. At this point number 1, the mass flow rate carry three type energy: kinetic, internal, and potential energy. So the mass flow rate of the fluid entering to the system carry three type of energy: kinetic energy at point number 1, potential energy at point number 1, internal energy at point number 1. Kinetic energy at point number 1 is half mass flow rate of the inlet fluid, and the velocity at point number 1 to the power 2. So similarly, potential energy mgz1. So mass flow rate of the inlet fluid, and g value of g is 9.8. Internal energy at point number 1, and the mass flow rate of the inlet fluid. Now from equation number 2, the inlet, this is equation number 2. This one equation number 2. Inlet energy minus outlet energy is equal to energy accumulated, energy entered to the system. Now from figure number 1, energy entered to the system due to mass flow rate is this, as we have already discussed. One energy is entering, three energy is entered to the system due to mass flow rate. Due to this mass flow rate, one is kinetic energy, the second one is potential, and the third one is internal energy. Similarly, some heat are also entered to the system. This is Q dot. Similarly, the shaft work is also added to the system. So these are the energy entered. To the system minus energy out. So three type of energy out from the system due to the mass flow rate of the outlet liquid. So mass flow rate of the outlet liquid leaving the system. Then this mass flow rate will carry three type of energy. One will be the kinetic energy, the other will be potential energy, and the third one will be internal energy. And energy entered to the system, this is the energy entered to the system. This one, 1, 2, 3, 4, 5. And energy leaving the system will be 1, 2, 3. This is energy leaving the system, and it will be equal to energy accumulated in the system per unit time. So change in energy with the passage of time, and the CV is the control volume. So open system is a control volume. It is also called the control volume. So this is also called the control volume. If the system boundary moves due to some work, now if we compress the system or if we expand the system, then the boundary of the system can be moved. So then in this case, if the boundary of the system are movable, or if we do some work on the boundary of the system, and if the boundary are flexible, if the boundary can move with forces, then what will be the work of expansion and compression work? So we will derive the expression for compression and expansion work. So if the boundary of the system are movable, then the work will be equal to In this case, W is the work, and this is the force, and this is the displacement. As we know that work is equal to force into displacement. So we know that force is nothing but it is pressure is equal to force per unit area. So force is nothing but it is the product of pressure and area. So in the place of force, we will write PA into dl. Now work rate is equal to, now we will derive the work on the basis of work rate. So work rate is nothing but it is work per unit time. So work per unit time. Now divide this equation. Suppose this equation, divide both sides by time. So W divided by time, it is nothing but the work rate, and work rate is nothing but energy. So work per unit time is equal to PA into dl divided by dt. So this PA dt dl into dt, this is the area and this is the length. So area multiplied by length. Suppose this is the area and this is the length. So this is area and this is length. So area when multiplied by length, we will get the volume. So this is the volume. We will write A area into length, when we multiply we will get volume. So P into dV divided by dt. So pressure into change in volume divided by change in time. So the volume can be decreases or the volume can be increases. If surrounding do some work on the system to compress the system, then the volume, then this dV will be decreased if surrounding some work on the system. Or if the system expanding with the passage of time, then this dV will be positive. So expansion work is positive and the compressional work is negative. So this is equation number 4 and this is equation number 5. These are the compressional and expansion work. So when we include the compression, we can include these two types of work in our energy balance equation. So similarly, there are another type of work which we can done on the open system. So similarly, if one fluid element exert force on another fluid element, then work can be also done. So suppose this is one element of the fluid, this is other element of the fluid. If this yellow element of the fluid exerts some force on this red or this element of the fluid, then work can be also done on this system, on this fluid element, with the help of this fluid element. So this yellow fluid element will do some work on this fluid element and it is known as flow work. So flow work is nothing but it is like P dV work. So W is equal to minus P delta V, or in compressional cases it can be minus P dV, or in expansion case it is P dV. So W is equal to P pressure, and this is the specific volume. Delta V is the specific volume. It is nothing but volume per unit mass. So this is the specific volume and this is the mass. So this is the PV. Again this is the PV. As in the denominator this is mass. This mass will be cancelled with this. So it is again PV. So W is equal to P delta V into delta M. And this is the flow work. Flow work on rate basis we will write dot. So P delta V is specific volume into change in mass. So this is the change in volume. Suppose this the volume of this element is delta V1. Suppose delta V, and the mass of this fluid element is delta M. So delta V and delta M. And this is the pressure. And the pressure is nothing but it is this pressure. At this position, the pressure exerted by this yellow fluid element, which is P1. So P1 at this position is P1. Or P, simply P, you can write as simply P. So this is again an open system. There are two positions. One is the position number 1, mass flow rate enter to the system, and the mass flow rate out from the system. This is the heat enter to the system, the sharp work done on the system. This is the internal energy, kinetic, potential energy, internal energy, potential, and kinetic energy V2, kinetic energy. And there is some there is some flow work. This is the one fluid element like the previous case. This fluid element exerts some force on this fluid element. So it will be written as fluid element work on fluid element number 2, that inlet position is limited by Wf1, and this is on the red base. So Wf1 is P1 and P1 is this one. This is the pressure exerted by this element on this element, that is P1. Similarly, this is P2, this is another fluid element, this is another fluid element, this fluid element exerts force on this fluid element, and this is the P2. So Wf1 is nothing but P1 into volume of the element 1, specific volume of this element, this element, this shaded element. So similarly, and mass delta m1, and this is the mass of this element. Similarly, Q2 is this pressure, and this is on this element, pressure on this element. And similarly, the delta V2 is the volume of this element, volume of this was element 1 and this was element 2. So volume of this element 2 is delta V2, and the mass of this element 2 is delta M2. And on the red basis there is some dot on this delta M2 and this delta M1 on red basis, and this is the z is equal to 0, this is the reference position, here z is equal to z1, here z is equal to z2. So, and this is our system, Now we can further simplify our equation. Now if we include the flow work and the boundary work, like in the compressional work, expansion work, and the flow work, if we include these three work in our energy balance equation, then what will be equation number 3? So equation number 3 will be equal to, now if we include the flow work, the boundary work in equation number 3, then equation number 3 will become equal to, this is the inlet mass, it carries some kinetic, potential, and thermal, this is the heat enter to the system, the shock work, this is the compressional work, this is the expansion work, and this is the energy out due to mass, or the mass flow rate which leave the system that carry with itself kinetic energy, potential energy, and thermal energy. And this is the flow work at position number 1, and the flow work at position number 2, and this is the energy change in energy and the control volume with the passage of time. So this is the flow energy at point number 1, this one, and the flow energy at point number 2 is this one. At point number 1, the flow energy is Wf1, and it is equal to P1 delta D1 V1 and delta M1. So this is the, now at steady state this term will be equal to 0. Change in accumulation will be equal to 0. Similarly, at steady state the accumulation term will be equal to 0. At steady state, at no flow work. Similarly, at steady state, when no accumulation, there is no accumulation. Similarly, if there is no accumulation, there is no flow work, there is no boundary work, then equation star will be equal to, what is equation star? This is equation number star. So if there is no work at steady state, this term will be 0. If there is similarly, if steady state, at steady state, if no flow work and no boundary work, so if no boundary work and no flow work, so at steady state, first of all, at steady state this term will be 0, and there is no flow work and no boundary work. No boundary work means no compressional work, no expansional work, this term will be 0. No flow work, this term will be 0, and no flow work, this term will be 0. Only this term will be appear. Input minus output. Input minus output, this one will be equal to 0. So similarly, in case of if shock work is also 0, and if the kinetic and potential energy are also 0. So if in some cases, if the flow is in the straight pipe like this one, if the cross-sectional area of the pipe is same, then in that case we can say that the kinetic energy is 0. Similarly, if there is no height if the flow is in a straight line, then in that case if the height elevation or change in elevation is 0, then in that case we can say that change in potential energy is also 0. So in most cases kinetic and potential energy are negligible. So then in that case the mass flow rate enter to the system, and the internal energy per unit mass or internal energy minus mass flow rate out from the system into the internal energy will be equal to 0. Similarly, from mass balance equation, if inlet mass flow rate is equal to the outlet mass flow rate and it is equal to mass flow rate, then in that case this equation, suppose this is equation number A, this inlet mass flow rate and out mass flow rate are equal and it is equal to mass flow rate. So in this case this equation number A can be written as mass flow rate into U1 minus mass flow rate into U2 is equal to 0. Then take common mass flow rate into delta U is equal to 0. This is equal to 0, so change in internal energy is equal to 0. So this is a very simplified form of the energy balance equation, and these energy balance equation, like this energy balance equation, this simplified energy balance equation, also this energy balance equation, we can use these energy balance on this type of instrument, this type of open system, and also on distillation column, compressor, expander, nozzles, expander. So we can use these energy balance continuity equation, energy balance equations for this open system. Thank you very much for your attention. Thank you very much.